Hello guys, a very happy morning to one of you. And now we are just going to see the next chapter in the production engineering. Okay. So in the previous thing, I just covered a little bit of extra things about each and everything. So without wasting time, let us get continued because I think so we no need any kind of explanation because at the before time I just told only the basics. Okay. So each and everything I think so you would have known. So just simple thing you can see. So v equal to pi dn by 60 meter per second. These are just a basic thing. Okay. So and it is meter per second. Okay, whenever it is given it means meter per minute means that 60 should not be there, and as well as the 1000 and each and everything I think so you can find. So next one is feet. Okay, feet equal to feet is f in mm per revolution. Okay, so f into n mm per minute. Okay, depth of cut is d equal to d1 minus d2 divided by 2. Okay, so that's it. Okay, so generally in the 2D it means in orthogonal machining you can see this is a, I'll just zoom a little bit. So you can see this is a relief or clearance phase, this is a rake phase. Okay, this is a shear angle, this is a shear plane. So the chip goes according to shear angle. Okay, I think so you got the point. So you can see this is chip and this is shear plane, cutting tool edge radius and b and velocity, each and everything is been there. Okay. Okay, so generally you can see positive rectangle. I just told you, anyways I'll just tell you again. So positive rectangle, this is positive rectangle, this is negative rectangle, this is clearness angle. So this is neutral angle and zero rectangle. So negative rectangle generally is used for cutting off so much higher. It means if the material has so much higher load, means for that we generally use time is called negative angle. Okay, so you can see negative rectangle recommended cutting tool is ceramic and carbide. Okay, but here positive rectangle the cutting tool is HSS. Okay, these are basic things I think so you would have known to know. Brittle metal generally used to cutting. Please adequate to this one. Okay, zero rake. Okay, single point, multi point. Okay, again I'll just zoom a little bit. I think so you are able to see this one. So this is the end relief angle, this is back rake angle. Okay, so this is right cutting edge, this is end cutting edge. Okay, this is thing is handling no side and side rake and side relief. Okay, next one is back rake angle alpha b. It is an angle between the face of the tool. It means it's on. So generally base of the tool and these will be in perpendicular base and parallel to the length. Okay, in positive back rake angle the chip takes away from the machine surface, while negative and the chip directly consider machine surface. Okay, okay, side rake angle, you can see this is the side rake angle. Okay, it is an angle between the face of the tool and the base of the tool, and it is usually parallel and perpendicular. Increase in the side rake angle reduces the chip thickness. Okay, increase in the side rake angle, like this will the chip thickness will be just reduced. Okay, angle of inflation on the rake face with respect to tool is measured, so it is side rake angle. Okay, this thing I just told you. And end relief angle, it is an angle between the portion of the end flank immediately below the cutting. So this is a basic thing because I don't need to explain so much because just normal thing is end cutting edge angle. The end cutting edge angle is the amount that the end cutting edge slope away from the nose of the tool, so that it will clear the finishing surface of the work on the workpiece when the cutting and side cutting is. Okay, suppose you can see this is end cutting edge. So generally end cutting edge doesn't have a contact with the machined surface. Okay, if it have any contact with the machine surface, then definitely it will be so much problematic to us. Okay, so next one is side cutting. In this one, it prevents the tailing edge of the cutting tool of the tool and from rubbing against the workpiece. The larger and the end cutting edge angle, yes, definitely guys, a larger cutting, this one if it goes to larger means it weakens the tool and it is continually kept between 8 degree to 50 degree. So side cut edging angle. Okay, it is an angle which prevents interference of the tool enters the work material. Okay, it's an angle which prevents interference of the tool enters the work material. Longer this longer this angle, the greater the component of force then it will supply the work control. Okay, yes, definitely. So side cutting edge is so much important. If you provide the longer angle means the separation will also occur and also the chatter sound, but like sound will occur. Okay, next thing is an increase in the value will have more length in action for a given depth of cut. Okay, at this increased value, it produces thinner and wider. Yes, definitely. Whenever you just increase the value, it produces thinner as well as wider chip to contribute the cutting heat. Okay, this also increases tool life. But zero side cutting edge angle is desirable when the machining, casting, and forging with the hardened scaling skins. Because of the least amount of tool, edge should be exposed to destructive action of the skin. Okay. So you can see next one, the tool life increases with increase in the side rectangle. Yes, increase in the side rectangle, it leads to decrease. Okay, tool life increases. So thrust force will increase with the side cutting edge. Okay. So consider the following statement: in orthogonal single point cutting tool, side cutting edge is being increased with tangent force and radial force. And so generally 3. Okay, tangential force, this doesn't have any kind of size. So longitudinal force and radial force. Okay. Next one is leap angle. Okay, so you can see leap angle or wedge angle or knife angle or cutting edge. It means cutting angle depends on the rake. So it means simple. So this is the, I think so, side rake, and this is the inside rake. So this is the leap angle. Okay, so this is the leap angle. Okay, that's it. So you can see rake and clearance angle is provided on the tool, determine the strength of the cutting edge. Okay, so a larger lip angle permits machining of harder machining surface. Harder the metals allows a heavier depth of cut and better heat dissipation and increases tool life. Okay, the angle between the face and the flank of the single point cutting tool is lip angle. Okay, face and flank of. Okay, this we can understand. So for drilling cast iron, the tool is provided with point angle smaller than the required ductile material. Okay, smaller point angle results in lower drilling. Okay, so we'll just see afterwards because it's given in the drilling. Okay, so next one is nose shade. You can see it is a curvature of the tool tip. It strengthens the tool nose by reducing the stress concentration. It increases tool life. Okay, curvature of the tool tip strengthens the tool by reducing stress concentration. Increases tool life. It provides better surface finish. But too long a nose radius will increase. Too long nose radius will increase. If the nose radius increases, the cutting force also increases. The cutting power. Okay. So tool life increases with increasing nose radius. Okay. So this is a formula H equal to F squared divided by 8 of R. Okay. So this is the average roughness. Whenever the nose radius is generally the cutting average roughness decrease. Okay. So you can see this one. Consider the following statement with respect to effect of rods. Okay, it reduces surface finish. Okay, okay, it increases possible. Yes, definitely. Whenever the larger nose radius increases, it increases the possibility of shatter. It improves tool effects. Okay. So in this 1 and 3 will be so. Okay, it reduces the cutting force, but it increases the cutting force. Okay. Tool signature. Okay, as I just told about what is the thing: back rake angle, side rake angle, end relief angle, side relief angle, side cutting edge, end cutting edge, end cutting edge, side cutting edge, and this one nose radius. Okay, so rake relief cutting edge. Okay, so this is the basic thing most of the times they will ask. And next one, side rake angle. You can see side rake angle, this one. So what is that? It's 6 is the side rake angle. Okay. So tool signature, you can see a numerical method of identification of tool. Yes, definitely. So this is the orthogonal rake system. Okay, so this is one of the other kind of system. So we will see in this. Okay, so you can see, I think so you can see this one. Constant now it's okay. can see as it is rotating, you can see workpiece hits here. Okay, it gives force downwards. So to push the tool upwards, so we need to provide a force. Okay, I think so got the point. So this side also we need to push, and this side upper also we need to push. Okay, so you can see 0 1 is a cutting edge, and cutting edge with the workpiece there is a contact with the force and the remaining tool. Okay, and to cut the workpiece of the tool moves forward in this direction. The tool moves forward. So that force is called as contact force, as well as cutting edge is perpendicular. So this contact force is called as thrust force if it moves in this direction. Okay, in the direction it is moving, it is cutting, it is which one? It is thrust force. Okay, so you can see now thrust force is this side and cutting force in upper. Okay, FC is cutting force. This mainly leads to removal of the top workpiece. Okay, I think so. As cutting edge tool and workpiece both in differently contact edge, so the force will always be perpendicular in direction. So thrust force will be 0. Okay, so it means tool and workpiece will have no contact. So next force analysis can be done where there is forces, but if forces are not there, we can't do any kind of analysis. Definitely whenever there is a force, it means whenever there is a force we mentioned, so we can definitely do this kind of thing. Okay, so you can see this entire thing, there are simply planes which tells the angle only, not forces. Yes, because if you just take according to machine reference system or tool reference system, each and everything comes, it means tells according to the angle only. Okay, it doesn't tell about the force. So but we need force only. So to measure all of this thing, not the angle, so we need to overcome this orthogonal rake system. Okay, so that's why you can see during measuring, it means measured force appears on either AC and around the cutting edge. Okay, perpendicular cutting edge. Okay, so but in the American Standard Association, the planes are neither along how to say means generally orthogonal rake system we just find the angles, but it means one is machine reference system, other one is tool reference system. Okay, so you can see for ASA used for EC analysis, for manufacturing a tool we can use this manufacturing a tool. Okay, ASA it is machine reference system. ORS used for force analysis. Okay, so it will be difficult. Okay, I think so you got the point. For force analysis, ORS tool signature is introduced, which is based on tool reference system. Okay, for force analysis, ORS tool signature is introduced, which is based on tool reference system. Okay, so you can see for force analysis system, ORS tool signature is introduced, tool reference system. Okay, ORS tool reference system stands for orthogonal rake system. Okay, this is the entire thing. Okay, so if I just want to tell means I'll just go to again. Okay, you can see it means here each and every plane we measure with reference plane, so the reference plane will be different. So here entirely based on machine reference system. Okay, American Standard Association is entirely for machine reference, so we'll just place the machine and according to the machine we just calculate each and every. So this ASA tool signature. Okay, so you can see therefore ASA angles can't be used for force analysis. Okay, so we need to measure the tool. So for tool we are just taking tool reference system is called the orthogonal rake system. Okay, so you can see this one, I'll just write it down. Let's just take another note. So okay, so now you can just see, I'll just zoom a little out. Okay, so you can see first is inclination angle. Okay, inclination angle. Second one is orthogonal rake angle. Okay, next one is side relief angle. Next one is end relief angle. Next one is end cutting edge principal angle. It is principal cutting edge angle. Next one is nose radius. So I alpha C lambda n. Okay, I is inclination angle, alpha is orthogonal rake angle. Okay, orthogonal rake angle. Side relief angle. Okay, end relief angle, side relief angle, end relief angle. So this one is end cutting edge. Okay, end cutting edge angle. This one is principal cutting edge angle. Okay, this one is nose radius. Okay, so this is the entire thing. Okay, so we'll just take the reference system. According to the reference system of the tool, we analyze the force. Okay, I think you're getting the point. Okay, so this thing means while just going each and everything I'll just tell. So you can say orthogonal direct system, only tool it says according to what is how the tool is built. So but over as orthogonal direct system tells the force analysis. Okay, so these are the so much big problem. This is not needed for you. Okay, but it can, the other thing is we need to convert the American Standard Association to ORS. Okay, it means entire tool is been converted to force analysis. Okay, you can see tan I equal to cos sigma s of tan alpha b minus of sin us tan alpha s. Okay, so while just going to each and everything I'll just explain to you. Okay, so now it is not needed that much. Okay, so next one is wedge analysis of the tool. Okay, so it's been shown in this in the events front view. Okay, you can see this front view. So this is the rake face and this is the side face. Okay, so this is the reference face. Okay, this is the orthogonal plane. We just took the orthogonal plane, so you can see this is the entire thing is orthogonal plane. According to orthogonal plane we are just taking. Okay, so rake face and this is side flank. Okay, so you can see this one is alpha is orthogonal rake angle. It means we are just calculating according to 2-dimensional axis. Okay, orthogonal rake angle, this one is alpha. So this one is gamma, side relief angle. Okay, rake angle we are just taking in 2 dimensions, we are just taking orthogonal rake angle, this is side relief angle. So theta is a wedge angle. Okay, so in case if theta wedge angle is so much smaller, you can see it is if it is so much smaller means simple guys, how to say means since theta is so much smaller, so the cutting will be, it means you can see the sharpness, it is so much sharp. But you can see when theta b is so much larger, it means the sharpness is not that much. You can see theta a is a red line cutting edge. Okay, and then cutting edge material is less and support and strength may be less. Okay, so theta b is material tip is more and more strength withstand more. So theta is a directly proportional strength of cutting edge. Okay, so theta increases, strength also increases. So which one is more shape? Okay, you can see theta directly proportional 1 by sharpness of the cutting edge. Okay, so generally theta is a wedge angle, it is called as slip angle. Okay, this theta is generally called as slip angle. This is orthogonal rake face rake angle, this is relief angle. Okay, so I think so you can see this one. So this definitely it means goes down, rake face goes down and relief and each and everything slope is being downwards. So this is parallel. Okay, this one and the slope is like this. Okay, that's it. I think so you are able to see this one. So positive rake angle, this one alpha theta equal to plus v, and this one is 0 rake angle, this one alpha not equal to 0, this one is negative rake angle. Okay, so alpha b orthogonal rake angle converted to rake angle. Okay, so I think so you can understand. So which tool will use for minimum? So definitely which tool, it means tool 1 will use so much minimum. Okay, but tool 3 it means negative rake angle will use so much of forces. So okay, so tool 1 will also have lesser power, tool 2 medium and tool 3 is higher power. It is stronger means tool 3 will be so much time. So it's a negative rake angle. Okay, used for cutting stronger and harder piece. So why this material can't be used for cutting lesser? Because it's a useless guys. Because you are a lion, will you go and hunt a small rat? Definitely no, no. So as it is, so since you are a lion, you have to just go and hunt an elephant or a wild beast or zebra like that. So that's why negative rake angle is not being used to cut a lower order material. Okay, power is electric energy equal to V into I. So will be same because late motors rotate at the same speed. Okay, so even though the negative rake angle is capable of machining very low strength workpiece, we don't use it because low strength materials have tendency to produce long ribbon chips. Okay, low strength material has tendency to produce long continuous ribbon chip. While the ribbon it means continuous chips comes out, the negative rake face will just add extra force. So this leads to the flow in the machine surface. Okay, machine surface will flow. So or the gap between the machine surface and the end flow. Okay, so there it will be rubbing, okay, as well as the tool ends I think so condition. So there is a maximum problem. Okay, so that's why we don't use the negative rectangle. Okay, I think so can understand. So wedge angle or lip angle, okay, it is an angle between face and flank of the cutting tool. Okay, so this is the entire thing. I think so can understand, just a normal thing. So this is also wedge angle, this is also wedge angle. So two wedge angle, no, definitely both are same. Okay, so you can see this one entire thing will be, it means orthogonal rectangle plus wedge angle or lip angle plus of the end side relief angle equal to entire thing is 90 degree. Okay, so next time if theta directly proportional 1 by sharpness or keenness of edge. Okay, and sum of total rectangle, sum of total. Okay, so each and every time you can see that this entire thing is theta and smaller is minus. Okay, each and everything, this entire thing will be 90 degree. So this thing I think so you should not confuse. So next thing you can see, while moving forward you can see rake angle increases or decreases. You can see while moving forward rake angle you can see it decreases. Okay, okay, while moving forward rake angle decreases. First positive, next is 0, next one is negative. Okay, so by grinding we change the rake angle slope. Okay, positive tool strength increases as well as sharpness decreases, force and power is also increased, theta is increases, and you can see this one positive rectangle workpiece soft and ductile. So tool is 40% strength, it should be HSS. Okay, negative rectangle machining hard and brittle, so carbide tools or ceramic tools. So negative rectangle to cut the harder workpiece generally we don't use. Okay, positive rectangle we use negative rectangle. So you can see at the beginning it will be, it means while it's been rotating negative rectangle, the workpiece rotates and the tool moves forward, there will be sudden impact. So this may break to little bit of reflex because it doesn't absorb. Yes, one of the most negative thing is negative rectangle doesn't have the capacity to absorb energy, so it breaks suddenly. So that's why they add negative rectangle material as well as the positive rectangle material. Okay, so you can see this entire tool bit is called as negative, it means it is brittle material. So you can see with the fastener we just screw it, and you can see, and with thread to adjust. This entire thing is high speed steel. Okay, the high speed steel has a, it means capacity to absorb a lot of stresses and energy. Okay, after time goes the edge may not be so correct, so it means we regain it, so we just tilt, it means we just rotate and we just do each and everything. Okay, so generally this kind of tool bits are generally formed by powder metallurgy. Okay, I think so you can understand. So negative rectangle always be between positive and negative. Okay, brass and copper. So you can see brass is soft, it means copper is soft and zinc is hard, and brass is this one, and cast iron +7 to -7, +5, plus minus 5 to -5. So the rake force coincides with the reference plane and has no slope. It advantages and applications be between plus and minus negative rake. So zero rake tool are used for cutting, machining positive to negative. So cast iron and during that separating. Okay, so you can see this is unmachined surface, this is machined surface. Okay, or unmachined surface is generally called as atmospheric surface because at initial it may be 15 millimeter. This one is not in. Okay, so next one, irrespective of the type of cutting operation, the perpendicular distance between the though the small thing is called the depth of cut. Okay, so machine surface, the direction should be given forward and backward, no direction should be given. Okay, next one is width of cut. Oh. So you can see this is depth of cut, this is width of cut. Okay, I think so you can understand. So you can see this is depth, this is width, and you can see, so this is side cutting edge angle. Okay, side cutting edge angle, and this one is principal angle, principal cutting edge angle. Okay, so based upon this you can calculate each and everything. Okay, this d width of cut, each and everything based upon angle you can just calculate. So next one you can see field and uncut thickness. Okay, for cutting there should be same relative motion. So this also need to rotate, this also need to move. Okay, here two relative motion, you can see the thrust force goes here and the cutting force goes upward. Okay, the relative motion between tool and workpiece, it means tool with respect to workpiece is called as, it means along the direction is called as feed. Okay, So feed, it means in direct, it means you can see the relative motion responsible for generating the cross section is called genetics. Okay, you can see this is the cross section is circular, this is genetics, while the relative motion responsible for directing the generated surface in a given direction is removal of material. So you can see, suppose if we just go in this direction, the removal of material occurs, so it is directrix. Okay, directly we are just removing the material. So generic means we are generating the surface, that's it. Okay, so you can see the tool, the entire tool moves with respect to the workpiece, so it means with respect to rotating workpiece, so along the directrix. Okay, directrix is cutting, directly cutting, so it is called as feed. Okay, so next one, material removal equal to cross sectional area into feed. Okay, generally contact the area and while pressing the removal takes place. Okay, so generally material removal equal to cross sectional area into area of this. So genetics generating the cross sectional area into directrix is feed. Okay, so we'll just see, it means still a little bit of extra things. Okay, because still time is there, so I'll just explain each and everything. Okay, so you can see this is genetics and this is directrix. Okay, this is developed surface, and shaping, it means you can see in shaping both are linear. Okay, so you can see this one, developed surface is circular. Okay, what is the developed surface? Circular. So this is developed surface. Okay, next one's feed is, yes, definitely feed in turning operation equal to per revolution. Suppose you can see, it means for example this is the thing, so it has been rotating. Okay, so now we are just cutting. Okay, while we are just cutting, it moves 1 millimeter, it means this it means this rotates. Okay, while it's been rotating, how much millimeter we are just going inside. Okay, that is the main thing. So okay, next thing you can see the chip, the chip will also will come out. Okay, this is the entire chip. Okay, so chip, you can see this is, okay, with means like this it will be, so like this is the width. Okay, so like this chip will be, and this is the feed, it means feed equal to so per revolution. So you can see this, how much feed we are just giving, that much cut it will just take it out. Okay, I think so can answer just a simple only. So uncut length, so you can see while the chip comes out pi, it means 2 pi r, so 2 pi r means pi d. Okay, this is uncut length. Okay, will there be perfect after cutting? No. So because while cutting, force generates and so stress and inputs is not equal to output. Okay, whenever we just see the top, you can see this is the width and this is feed. 1 mm per revolution. So you can see 0 to 1 mm, 1 revolution or 1, so it's just a depends. Okay, so next one, so thickness mainly depends on the feed. Okay, yes, definitely thickness mainly depends on the feed, and if feed increases, thickness also increases. If feed decreases, thickness also decreases. Orthogonally, and each and everything is taken according to the orthogonal plane. Okay, so this orthogonal view, you can see, if the feed experienced by the cutting edge, it is perpendicular, it is called as 2 feet. Okay, we need to cut the actually F1. Okay, but we catch some thickness. So generally you can see this is the extra formula. So you can see this is the triangle, this small triangle. Okay, you can see this is the feed. Okay, So this here to here, so you can see this is the yes, definitely this is the feed. Okay, and this is the thickness. Okay, and this is okay, this is the principal angle, this side getting here. So while you are just taking each and everything, I can say this d1 by f. Okay, uncut thickness d1 equal to f of sin theta. So width of cut is d divided by cos of sin of x, cos of sigma x. Okay, this uncut thickness each and everything. Okay, so generally it means in orthogonal cutting we just put theta equal to 0. Okay, w equal to d divided by cos theta. So w equal to d. Okay, d equal to f of sin cos theta, t equal to f. Okay, so in orthogonal cutting only we just take this, but in normal we are just taking like this itself. Okay, like this we are just taking like that. Okay, so I'll just explain you this one again. So just a basic thing I just want to tell to you. So I'll just explain this one. So formation of chips in ductile material. So you can see while the chips being outside, you can see ductile material forms in the ductile material. You see while the tool is being here, so lot of compressive stress will be, so lot of force will be. You can see VC is down and Newton's law, tool also moves up. So at center there will be lot of huge compressive stress will be. Okay, so if we go up, it means if we go up in the force reduces. But due to compression, this leads to shear stress also. It means at different angle, magnitude is also different plane. Okay, so then there exists a shear stress in one plane which is more than the shear strength of the workpiece. Okay, there shearing takes place. Okay, so shear stress basically function of atomic attraction and repulsion. Okay, so lot of angles will be in that particular angle, you will just shake the shear. Okay, at this plane the shearing starts. Okay, this is called a shear angle. Okay, the central plane is shear angle, and there will be compressive stress at the material point where the material moves out of the shear plane. Okay, the material, it means compressive stress decreases. Okay, so I think so you can understand this one T1, this one is T2. Okay, T2 is the average chip thickness. Okay, so you can see this 5 Newton while it's been going outside, the stress decreases. Okay, that's a simple thing. So after coming in the chip layer, shearing stops. Okay, next layer again continue. The workpiece chip material, it means fully separate, not happening in the chip layer, not separate in the ductile material. Okay, so this is how continuous chips forms in a ductile material. Okay, so the chips moving leads to rubbing of the rake faces. Definitely it leads to the brighten. Okay, while it's been moving against the thing, so bright and burning surface, so it will be so much shining. Okay, so 5 Newton to 10 0 Newton will just okay, this is not okay, but think there will be shear strain. Yes, definitely there will occur a shear strain also, shear strain and shear stress also will occur. So due to the shear strain, the chips tends to become high. It means a little bit expand due to the shear strain is due to bigger chip. Okay, so you can see while it's been moving, it is bright and plain. So this is a previous model of chip function. Okay, during machining of the ductile material on the cutting edge comes in contact with the workpiece heated, it can compressive stress is generated, appears on the workpiece and material just ahead of cutting edge. Okay, as the magnitude of the compressive stress increases, shear stress appears in the material just ahead of cutting. Okay, so this entirely goes in a shear plane. Okay, that's it. So you can see it's continuously results. Okay, now it is cutting it, so this continuously takes place, so continuous chips will be formed in the ductile material. Okay, so I'll just explain these kind of things in later on video. Okay, I think so you understood the point. Let me see the next video. Until then, take care, bye bye, have a good day.